Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 24th, 2025, about 2 days ago. It introduces terminal velocity matching, a new way to train one-step and few-step image generators in a single stage, reaching 3.29 FID, with one function evaluation on ImageNet 256 and 1.99 FID with 4 evaluations, with similarly strong numbers at 512 resolution. The paper is titled Terminal Velocity Matching, and as we will see later, the implications for fast, high-quality generative models are quite significant. Alright, Figure 1 contrasts how different methods move noisy data toward clean images and also showcases sample quality. The left side illustrates that terminal velocity matching steers the trajectory using the terminal velocity near the endpoint, instead of the initial push used by flow matching or mean flow, so the path is optimized where images finally land. Colored arrows distinguish the predicted velocity from the actual model path. On the right, a grid of ImageNet animals and scenes demonstrates that a single function evaluation already produces sharp, diverse images at 256 and 512 resolution. So while Figure 1 contrasted sampling behaviors and visual quality, Figure 2 explains how terminal velocity matching works along a trajectory. The left panel shows the ground truth flow from noisy prior x1 to clean data x0, with a solid curve as displacement and orange arrows as the true velocity field. The right panel adds the model in purple, which jumps directly from xt to xs in one step, while matching the terminal velocity along the true curve. This match ensures that a single step lands on the correct point of the underlying continuous flow. While Figure 7 compares how stable training is for mean flow versus terminal velocity matching under classifier-free guidance. The left panel shows that the gradient norm for mean flow spikes wildly, while terminal velocity matching stays low and smooth. The middle panel reveals a similar story for the model velocity norm, which remains stable for terminal velocity matching. The right panel tracks FID over training, showing that constant guidance strength gives the best and most reliable convergence. Alright, while Figure 7 focused on training stability, Table 2 presents the bottom line for 512 resolution ImageNet. Diffusion-style baselines need tens or hundreds of function evaluations to reach FID around 2 to 3. In contrast, the terminal velocity matching XL2 model reaches FID 4.3 with just 1 step and 2.9 with 4 steps, which matches heavy diffusion transformers using about 500 evaluations. So while Table 2 highlighted 512 resolution, Table 1 reports results on ImageNet 256. The upper block shows classic diffusion and flow models needing about 250 steps to get FID near 2. The lower block compares one-step and few-step methods trained from scratch. Mean flow reaches FID 3.4 with 1 step, whereas terminal velocity matching XL2 improves this to 3.3. With 4 steps, terminal velocity matching drops to about 2.0, rivaling or beating many 250-step diffusion baselines at similar parameter counts. Well, while Table 1 summarized sample quality, Figure 10 studies efficiency in terms of runtime and memory. The table shows that mean flow with naive attention runs out of memory, whereas mean flow with a custom kernel trains in about 0.8 seconds and under 50 gigabytes. Terminal velocity matching with improved diffusion transformer costs more memory and time, but detaching the Jacobian vector product cuts step time to about 0.7 seconds and lowers memory use, making training far more practical. So while Figure 10 summarized end-to-end training costs, Table 5 zooms into a single attention operation with the new Flash Jacobian vector product kernel. The table lists latency and peak memory for different head counts and sequence lengths. Across all settings, the custom kernel uses far less memory, often cutting usage by an order of magnitude. Latency is also lower, with speedups that reach roughly 65%, and the vanilla implementation even runs out of memory on the longest sequences. Terminal velocity matching shows that one-stage training can deliver near-diffusion-level image quality in just a few steps, thanks to terminal time regularization and efficient Jacobian vector product attention. The broader implication is faster, cheaper generative models that still come with distribution-level guarantees. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.